Prasad, if you'd like to join the stage.
Yeah, thank you, Andy, for introducing the topic. I'm going to talk about how we try to realize this dream of unconstrained manufacturing. Andy set a problem at the very beginning. We can optimize, but sometimes we can't manufacture on conventional Jacquard and various machines. How do we move forward? So we decided at the very onset that we move away from conventional machines and actually do a bottoms-up approach. You have this architecture, and how do we deliver to manufacturing? So we use robotics and flexible automation to do that. So we work with Nottingham and also with other partners in the hub and our industrial collaborators on various aspects of the project. So essentially, we take a building block approach. We take modular robotics and create a loom or create a winding machine, create a braiding machine to deliver exactly what we want. And in doing so, we have come up with various architectures. For example, there's a multi-axial woven architecture, a cylindrical 3D preform, or an ultra-thick multi-axial preform, essentially to push the boundaries of manufacturing. For example, if you're familiar with the weaving technology, conventional Jacquard weaving looms have been programmed and adopted with appropriate creels and tensioning systems to create what we call 3D weaves, by which we mean creating multi-layer fabrics with various binder architectures. And also by creating slits and pockets, you can create what we call origami-like structures, T-sections, pi-sections, and various reinforcements that some of you are familiar with. So with this technology, as you can see, typically this was designed for making a broad woven cloth, typically out of cotton fibers, for example, in the textile industry. We adopted and modified to weave carbon fibers, but not quite to have the ability to do true three-dimensional structures. For example, in a woven fabric made of the Jacquard machine, we are restricted to knot 90 configuration along with Z binder fibers, and limited three-dimensional capability, limited thickness, and mainly certain origami-like shapes. So the first step is to how do we overcome this limitation? And in braiding, or what we call cylindrical type of structures, we looked at two types of structures. One is like a planar or that kind of structure. Second is closed surface structures like tubular kind of structures. Both find applications in composites extensively. If you look at braiding, whether it is a conventional maple braiding or radial braiding, you create essentially two-dimensional single-layer cloth in a tubular form. So if you want to make a composite, say, propeller shaft or something like that of a decent thickness, you need to braid back and forth to create a sufficient thickness. So that would mean these are two-dimensional layers, so interlaminar properties would have some problems. So what we try to do within this program is to work on two different manufacturing platforms. One is 3D weaving type of structures. Second is 3D braiding-like structures. So the objective is to create truly three-dimensional integrated structures with multi-axial capability. That means you can put 0, plus, minus theta, 90, any orientation you like. So that suddenly removes the manufacturing constraint significantly. And try to make near net shapes with variable tau densities. So you can actually, almost like 3D printing, you can define, I want fiber orientation and density of fibers in this region, or I want thickness this region. We should be able to develop the machine and program it accordingly. Similarly with 3D braiding as well. Looking at the journey of 3D weaving, we started working in 90s at Manchester used an old Lancashire loom with a Jacquard engine at the top to create three-dimensional architectures. And we learned from this, and around 2012-14, we set up Dornier with a Stobly Jacquard loom and started modifying the machine to increasingly create what we want to create. But within 2-3 years, we reached the limitations. We were able to produce quite interesting structures, but we cannot go beyond a certain point. That's when we started actually conceptualizing and developing a robotic 3D weaving process. And that's what this slide shows, a multi-insertion three-dimensional weaving. And this technology has been patented both in Europe and US. This gives a combination of multi-insertion weaving. So that means instead of building layer by layer, we can put up to 22 weft yarns simultaneously into the fabric, and we can also sculpture it. We can change the thickness, width, and so on and so forth. Just to give an example of a kind of a structure you can make is for example, a T-section coming out of the loom as a kind of a protruded kind of a beam. You're not actually making an origami and opening it up. In doing so, actually, we cleverly incorporated off-axis fibers. For example, the so-called angle interlock bind yarns becomes the plus-minus yarn in the vertical section, and that's where we want. So we can create multi-axial configuration, and also the important thing is the noodle section, so-called noodle section that we normally have in origami structures does not exist here. It's a uniformly thick structure with everything fully integrated. What it means is this structure not only improves the fiber architecture, it will also improve the off-axis loading. That's one of the major problems with conventional 2D composites, where when you try to apply off-axis load, you experience delamination and all sorts of things. But here, being truly integrated, almost like a billet-like shape, you can postpone significantly the delamination problems. There's an example shown where we have been weaving a T-section coming out of the loom. And we also worked on the platform where we create near net shapes using what we call robotic fiber placement, stitching and tufting technology. I'll come back to it in a moment. And then we have been working on another platform, what we call Quasi 3D winding, working with a company called Signet TechSkim. They launched this 3D winder based on the concept that we work together. And what this creates is not 2D layers, not through 3D, but it's what we call Quasi 3D, where individual tows have quite a complex geometry. And there is some kind of, not interlacement, embedding between different layers. So you get better damage tolerance in this process. And then we developed what we call quadriaxial braiding, where we put triaxial braiding with a hoop winding, again to open up the limitations of the braiding process. And then using that as a basis, we started developing what we call a 3D braiding technology, where we could combine the concept of helical winding and through thickness interlacement. This is a small desktop machine, and this is being scaled up to a much larger version to create what we call cylindrical preforms. It doesn't have to be perfect cylinder. It can be box section, any closed section with variable shapes, with multiple layers with through thickness binders. That's what we're trying to achieve here. Just quickly to highlight, we have 4 PhD students working alongside, especially to exploit the technologies that are developing between Nottingham and Manchester. And Sarvesh Dhiman has just finished his PhD. He looked at the effect of binder configuration on the residual stresses developed during the composite manufacturing process. Jinseng Park actually developed quite a complicated machine for fiber hybridization and micro wrapping, commingling, stretching, all sorts of clever techniques we can do to mix dissimilar materials and create 3-dimensional composites. Quasi Sauro has worked along with three-dimensional weaving and essentially studying how the binder architecture and binder tensions affect both the permeability and stress distribution within the composite, how the damage starts and evolves. Syed Abbas is almost in the middle of his PhD, is using robotic preforming driven by computer vision and deep learning. He developed these algorithms to actually learn the fabric architecture and start identifying individual unit cells and assign parameter geometries. And essentially, you can continuously monitor during the manufacturing process and optimize and remove any possible defects. So that's the primary goal of our manufacturing platform. And my colleagues, Vivek Konchuri and Shankar Roy, towards the end of this webinar, will actually demonstrate 2 case studies demonstrating how these technologies are used in that product demonstrators. Thank you.